What's good, everyone, and welcome back to another video. With my last video, I didn't talk about different structural type of binary trees. So with this one, I'm gonna make a quick video on it and then move on to DFS, BFS, and BST. Anyway, so if we look at it, a plain binary tree, which is like the baseline, the most general version is that every node has at most two children, the left and right. Left and right. And so there's no other rules on it yet. However, when you add those extra rules, it shows you like the different structural type of binary trees. And these are all about shapes, so nothing about the values. All right, so let me erase this real quick. Let's first look at the full binary tree. So a full binary tree by definition is every node has either 0 children or 2 children. No node has only one child. So when I draw it out, it'll look something like this. Boom, boom. 4, 5, 6, and 7. So like that. So as you can kind of see, node 1, 2, 3 each has exactly 2 children, and that 4, 5, 6, 7 all have 0 children, which is just the leaf. This would be a full binary tree. Now, an example that is not full would be something like this. Well, let's keep the 3, for example. There. See, as you can kind of see, node 2 right here only has 1 child, which basically makes it not full. So there's that. Next, we have let me just go back to, there we go. Now we have a complete binary tree. Now, a complete binary tree, or a binary tree is complete if every level is completely filled except maybe the last. And the last level nodes are as far left as possible. And what I meant by that is, I'll give you a quick example of how it looks. Let me erase it. There we go. This would be considered a complete binary tree. You can kind of see that level 0 is full. Level 1 is also full. However, level 2 isn't full, but it is filled from left to right. So you just gotta know that it will be complete as long as the last level is filled left to right. And that every other level before it are all full. And so there's also like no gap in the middle, which means it's complete. Something that would be incomplete or not complete would be something like, let's say we have something that looks like this. You can kind of see that this side is, there's nothing here, meaning it's not complete. You're not filling it from left to right. Yeah, so the last level is not filled left to right. Why this kind of matters, something like heaps or priority queues are stored as arrays using this property. And what else? Like index math only works nicely if the tree is complete. So you would want this to be complete. Now, there we go. Let's go to the next one, which is perfect binary tree. Now, a perfect binary tree would be something like all internal nodes have exactly 2 children and all leaves are on the same level. So it's basically full. It's basically full plus complete and plus symmetrical. Like it has to be completely symmetrical. So this right here is perfect because every internal node has 2 children and that all the leaves are on level 2. So all the leaves here are on level 2. So, and this is something like, if it's perfect, you can instantly sort of like tell, or you can do like let's say if say the levels is a perfect, but and it goes all the way down to like, let's say level is what, 0, 1, 2, 3, 4, 5, level 5 or something. And then like the values is different. It's asking you how many nodes are in there. You can just do a quick like equation, right? Which is H equals, or not H equals, sorry. Number of nodes is equal to h to the power of, no, not h, 2 to the power of h plus 1 minus 1. H would be the height of the tree, of the perfect binary tree. And so let's say, I mean, like, just taking this as an example, this binary tree would be the height of 2 because we're looking at this as like a level. So there will be level 0, 1, 2. So when that happens, let's plug it in. It'll be 2 to the power of 2 plus 1, which is 2 to the power of 3. That's 8 minus 1, which is 7. And as you can kind of see, the very last node is 7 because I did it in number order. So there's that. And then as you say, if there's a question that does the same thing, asking you the number of nodes in the perfect binary tree with, like, I don't know, level 10, for example, then all you have to do is just use this quick equation and then plug the 10 in, do the math, and you will be able to figure out how many nodes are there without ever counting them. And so, yeah, there's that. Now, there's another interesting sort of like binary tree, or people call it the skewed or degenerate. People also call it degenerate binary tree. I prefer skewed though. So for these are a skewed or degenerate binary tree is one where each node has exactly one child, so it looks kind of like linkless. A perfect example is if I just erase this, this would be a skewed. If I want to do the other side, this would be a skewed. Every node has one child. So obviously it's not good because when you do something like that, it looks kind of like linkless. So, and it's not really good because it's also like a very unbalanced tree. And when that happens, it's sort of like giving you it's sort of like a worst case scenario thing. So operations, let's say like you want to search, insert, it can go down to a big O of N. So just keep in mind, if a tree is unbalanced, then the time becomes big O of N. Yeah. And this is what happens when your tree is technically a tree, but behaves like a very sad linkless. Out. Anyway, and then, there's the balanced binary tree, which a tree is balanced if its height is big O of log N. So roughly the left and right of subtrees of any node aren't wildly different in height. And so if it's balanced, tree height grows slowly with number of nodes. Unbalanced, the tree can become long and skinny. So kind of like what I did with the skewed and degenerate binary trees. It looks very long and just very skinny, like a linkless. And again, why do you care? A balanced tree can get you to big O of log N when it comes to search, insert, or delete. However, an unbalanced tree can degrade it into just big O of N, and that's not good. So examples of data structures that sort of like enforce balance are like for example, AVL tree, or the red-black tree. Yeah. And many others, of course. But in like the ones I mentioned, I'll probably make a video out of them since they have their own things to do. But yeah, that's basically it for the different like structural type of binary trees. In my next video, I'll talk about DFS, BFS, and maybe BST as well. But yeah, thanks for watching.